Okay, so I'm going to try to record this session. I prepared a couple hours worth of material, and the first set of it I'm going to definitely cover because it's kind of my sense of what's most important in the class and by extension in the exam. And then I have a bunch of sort of modules, each dealing with some topics we've covered in the course of the semester. And I could go through each of those, and I have picked out sort of slides or put together custom slides for this review that I think contain the most important points about each of those sections. And I could go through each of those, and by the end of the 2 or 2.5 hours, you should get a sense of not only what I think is most important, but the most important points which are likely to be covered in the exam. On the other hand, I'd also be glad to use, after sort of the initial overview of what I think is important, I'd also be glad to use that time for questions that you've brought. So if you have questions that you would like to ask, those would be my top priority. And so I suggest that if you want to ask questions about any material I'm covering while I'm covering it, while this may be a very presentation-oriented session, just raise your hand or say something, and I'll try to address your questions. Okay. And if you want clarification on any of the text, please bring it up. I'm trying to record this session so that we can share it. The 371 review, it didn't go so well for my recording, but some others stepped in with smartphone recordings that really helped. In this case, I've tried to avoid the same problem happening by pointing it to a different place to record, so hopefully we'll have better luck. So I'm hoping this will have a good record of what's going on here. Okay? Now, what can you expect about the exam in general? Sort of what types of things will be in the exam? Well, you can expect with confidence a couple things. Okay? There's going to be quite a few short answer questions. Not multiple choice, but fill in the blank or list three major advantages that Scala offers compared to Java or something like that. So there's going to be a fair number of those short answer questions. Some true false, some fill in the blank with individual words, and some list 3 reasons of this or 2 reasons of that or whatever. Beyond that, and more so than in 371, for example, for those who have been in both, there's going to be some examples of code or specifications where I'm asking you to reason about it, asking you to interpret what it means. I'm asking you to indicate if this class is a safe subclass of another one, or if this subtype adheres to the promises of its supertype, and that those examples I might ask you to reason about and provide answers on, where you really have to study what's presented here. I might ask you what that code does. What's the function of this? There will also be a small set of questions which ask you to attempt to write down a little bit of code that will do one thing or another. Okay? And in that area, I'm not going to be really picky about syntax and mark you like a compiler would. You forgot the semicolon, or you have an extra semicolon or something like that. I mean, I'm not going to be really worried about that. And it's not a really big deal if you forget exactly whether it's a equals greater than sign or a a dash greater than sign to indicate a function in Scala or something like that. But basically, I'm going to be asking you to write a bit of code, and I'm going to be looking at sort of how you did it. And the most important thing would be sort of you're using the basic ideas, and the syntax is going to be less important. Okay, less important. I have tried to shy away from sort of memorization of exact keywords used in this place or another, or precise memory of exactly how in Python you do this versus Scala you do that in terms of the syntax. Okay, but I do want you to have some understanding of some of the high-level concepts of the differences between these languages and Java and C, etc. So I've tried to really put it on the conceptual side rather than the details of the syntax or exact memorization of the keywords. The exam hopefully will allow most of you to elect to finish early, but normally there are some people who go over it carefully to the end. I'd be surprised if people find themselves writing desperately to finish all the questions at the end. It's more if they want to review it and so on. Okay. That's sort of a high level overview of the exam. In light of this, there's going to be some questions which do have more weight than others. So I would suggest you scan through the exam to look for the questions which carry a lot of weight, and try to focus on them early if you can. So I will be there for the exam, with the exception of, and I say this at some pains because I can only think of one other exam where I've ever been absent during even a piece of it. But I will have to pop out for a small piece of the exam and then come back in. Okay, but I'll be there for the beginning and I'll be there for the end for what should be about an hour each. But probably in that middle hour, I'll have to go see a dean about some things. So apologies about that. I really don't like doing it. But what it does mean is, if you have questions, it's good to ask them early, or anticipate that I'll be back and have it done. I'll have someone standing in for me. It goes without saying, right? I'm not going to be watching you on webcam, but I won't be there 100% of it. It will be closed book, and I don't expect any calculations, that sort of stuff will have to be done. You won't be doing any numeric stuff that I could think of. Yeah, that's good. Okay, so any questions about sort of broad features of the exam? I'm glad to answer questions about it. No? Okay. So I'll give this session, and I'll tell you what I told 371 not so long ago here, which is normally these sessions give a pretty good idea of what I think is important, and by extension what's on the exam. And every time I give them, I walk away feeling I've given away the show, and then a couple days later, as I'm marking the exams, I lose that conviction. But what I will say unquestionably is that if you pay attention carefully to what's going on here and you ask questions where you're confused, I think you'll get an enormous amount of value out of it. I feel uncomfortable if there's something that ends up on the exam which I haven't mentioned at some point. And often you'll find me sort of talking through things which are the important concepts on the exam because they're important to the topic. Okay. Just so I don't disturb fellow folks. Maybe I'll unlock this guy so people can come in. Okay, so I have prepared a list of what I consider important themes or areas that we've covered in this class. And I'm going to go through those at first. Those are the must-haves. So we covered a set of languages, and those include Aspect J, Scala, Python as sort of novel languages. It's not that I expect you to know all the details of that language, but I do want you to carry away some sense of some interesting features of those languages, some things that distinguish them, some things which are attractive about them, and have some sense about how they compare with each other. And we did talk a fair bit, although in a more diffuse way than I would have liked, about sort of cross-language comparisons, things that are difficult in one language and easier in another. There's this thing called, which I didn't mention in class, called the no free lunch theorem. And that is, there's no, and that applied to this area means there's no one language that is better for all problems, okay? And often you'll get certain languages which are more natural to express certain types of computations, certain types of issues. And these three are each examples of languages which excel in certain subdomains, but they each have certain shortcomings, certain challenges associated with them. Now, what do I mean when I say I don't expect you to know all the details of the language, but I expect you to know some concepts? Well, each of them has a very specific syntax, right? Each of them has certain rules governing it. And I don't expect you to have a perfect knowledge of those for the exam. I view that as quite under important. After all, many of you will go and code in these languages, perhaps in coming months, but you'll have example code to look at, and you'll remind yourself of how you indicate this or that. But I do expect you to know about some broad features. Let me rattle off a couple, and I have slides filled with these things coming up. Scala, what would be notable about Scala? Anyone? What's some things that are notable about Scala?
Functional aspects.
Okay, yeah, it has really good support for functional programming. It has support for higher order functions. What does that mean, a higher order function?
Function built upon other functions.
Okay, yeah, so yes, let's sharpen that. We could say a function builds on other functions if it calls off to them, but that's not what you mean.
A function that can take a function and return a function.
Yes, it could take a function as an argument, or it can return a function as an argument, or both. So it's a function that operates on functions, takes one in, and maybe returns one. So it may be in a differentiator function. It takes in a function to differentiate, a place where to differentiate, to take its slope, right? And it returns back a function that given actually, it just takes in a function and returns a function, and that function that it returns, you give it a number about where to differentiate it, will turn back the slope of that first function you gave it at that point. So it is operated upon that function you give it. You give it the function, you give it a function sine, and it returns cosine. And that's an example of a higher order function. So good, that's part of Scala. It really has good support for this. What's another feature of it? It's another important feature of it.
Runs on the JVM and can support Java libraries.
Oh, great. Yeah, runs on the JVM, can support Java libraries. It's interoperable with Java libraries. You can call Scala code from Java and vice versa. In fact, there's a whole swag of types in it that are Java types that you can use very directly and import into it. So that's good. And it's on the JVM. We'll come back to that issue. What's another feature of it? So it runs in this Java virtual machine. But what's another feature of it?
So we need to give explicit types.
Yeah, it does type inference. It kind of figures out a lot of the time what types you mean by something. And that makes it really easy compared to Java 8 in specifying some things. By the way, I should really put, well, here, what the heck? I should really put Java 8 here because I do expect you to know features from Java 8. And we'll probably come to covering some of those important features later. But compared to Java 8, Python is eminently readable because you don't need all these by function things and operator of less than, greater than, with the type in the middle and so on. So it does a lot of type inference. It figures out the types for things and it cleans up your code a lot because of it. It can't do it perfectly, and there are some types you want to put in, but it fills in a lot of the gaps, which is notable. What are some other features? Turns out it has a feature that I hope does not afflict any of you. Begins with an L, ends with a Y.
Lazy?
It's lazy. It's lazy. Okay. And it actually supports laziness in two different ways. In a way called by name. You can have an argument, and the argument, the parameter, it encodes sort of how to compute something. So every time you use it, it recomputes it using that formula, that way to compute it. Every time you refer to that parameter, it actually uses it. And if you never refer to it, it never computes it. It's one way of laziness. Another way is there's actually this lazy keyword, and it's by need. So it's not until it's needed that it computes it, but once it computes it, that's its value. It doesn't have to compute it again. It got it once, okay? So yeah, those are some nice features about Scala. Very nice features about Scala. They're not the only ones, and I'll come to some later in my slides. I'll be giving you all these slides. We'll put them up. Python, what are some features of that language that are really quite distinctive? Quite sweet in some cases.
Goes by white space.
Yeah, it uses white space. White space means something. It's part of the syntax of the language. Whether or not something's indented, we care about it when we read code. At least, I hope everyone in this room cares about it, because we after reading a lot of code, we often implicitly depend on that white space, are counting that this person is adhering to these white space conventions in language like C or Java and Scala, etc. But with Python, it's actually part of the language definition. And so the white space is enforced in a certain way by the interpreter. It means something different if you don't invent it than if you do. And Python, because of that, it can clean up your code some. Why is that? Well, you can, for these certain clauses, you can leave out the begin curly and end curly that you need in a C-like language, right? The white space does it for you. The fact that this is all indented, you can kind of, the interpreter can tell, and you can tell sort of at what logical level it's included. Okay, what other things are kind of nice about Python? Kind of distinctive.
It's loosely typed.
Yeah, it's loosely typed. Loosely typed. In a certain sense, and not in others. Okay? You will find things that will actually say that Python is strongly typed for values, but not for variables. This is an important distinction, because often we think of a variable as having a type. This thing called P always refers to a person, And in Python, that's not true. P could sometimes point to a person, and sometimes it could point to a pineapple. I am okay. Sometimes to a porcupine. Sometime, ladies and gentlemen, to a pickle. And sometimes to an integer, which is a most prickly combination, actually. But the point is that the variables are loosely typed in the sense that sometimes they could be bound to one type of thing, sometimes another. Sometimes a string, sometimes a number. And that's pretty loosey-goosey. That's one sense in which it's loosely typed. There's another sense, too. which is that it uses what's called duck typing. Which is also somewhat loosey-goosey. And some people even feel it's for the birds. But what does this mean, duck typing?
If it looks like a duck, it's a duck.
Yeah, if it looks like a duck, if it quacks like a duck, we'll treat it as a duck. And what this means is it's not going to require your code to force into maintaining rules about this code can only take something that matches this interface or that's an instance of this class. You know, in Java, we'll do that, right? We'll say this variable, whatever it points to, maybe it just points to something that implements some interface. We're not sure exactly what class it is, but it has to implement this interface, right? And because it implements that interface, we can call foo on it. And in fact, bar. It supports foo and bar. And we're counting on that. And if you try to pass it in something that has foo and bar in it, but it doesn't support that interface, it will be unhappy. It'll say, well, you don't support this interface. And so, you know, a beginner in Java could be excused for saying, well, wait a minute. I mean, it supports foo and bar. But they've missed the point. It's actually not a matter, are those functions defined? It's, are those functions defined as they relate to that type, that interface, or that, it can be a class. And so Java is quite picky about that. And a lot of languages are. C++ the same thing. C# the same thing. They have to implement a certain type to be accepted by the compiler as sort of a legitimate target when you call foo and when you call bar. It's going to say, does that thing support the right type? And if not, it'll warn you. It'll tell you. But with Scala, with Python, it'll just ask, hey, does this thing support a foo? Does it support a bar? In short, does it quack? And if so, it'll say, well, that's fine. As long as it supports a foo, that's fine. Oh, here, it requires a bar. Does this thing have a bar? If so, it's fine. It's not going to be picky about whether it's, you know, this type or that type. As long as it supports those, it's fine. So it uses this duck typing. And duck typing has some real trade-offs about it. Now, you could view it as kind of a loosey-goosey form of typing because it's not insisting on that it be a certain type. So if we say o.foo, it's not insisting that O be a very specific type here, right? And it'll just, if it has a foo, with the right number of arguments, it'll be just fine. It'll be hunky-dory. So in that sense, it's loose as well. Was it Peter who said that? Yeah. Okay, what other sense, though, is it not loosey-goosey? Well, it turns out that values there, so if there's an actual value, 3, a certain string or whatever, those things aren't turned into each other willy-nilly. So if there's something that needs a number and you give it a string, quote, 3, it doesn't automatically convert it. It doesn't say, oh, I know what that is. That's a number 3. I'll turn it into a 3, and now I can add it to 5 or something. It does not do that. So in that sense, it's not as loosely typed as some other languages are in sort of allowing you to go between different types, automatically convert from one to the other, which may sound attractive, but it has some real shortcomings. It has shortcomings in the sense that sometimes it hides errors. You didn't mean for this thing to have a string, but it's going ahead and accepting it blithely and doesn't even tell you. Okay, what's another feature of Python? Well, it is interpreted. It's an interpreted language. What that means is it's not going to be checking your code ahead of time to see if you've given the right number of arguments to things, if you've used the right types, if if the syntax is right, if you forgot to capitalize something or forgot to make this wild keyword lowercase, it's not going to check that ahead of time. When is it going to check that?
When it runs.
When it runs. It's going to be checking it when it runs. And that has some flexibility, and it has some, so it has some advantages and has some disadvantages. What's an advantage of that?
You don't need to compile things.
Yeah, you don't need to compile it ahead of time. In fact, you can kind of piece together your program dynamically. At different times it could load different code in from different places or what have you. So that's good. What's another advantage of it? Being just an interpreted language.
If an error doesn't come up, it won't necessarily happen.
Yeah, so it based on the flow, there may be an error in there, but maybe that's only enabled during debugging. It's only, that part is only enabled during debugging because debugging is disabled. This is shipping code. It'll never get there. And so that error, while it's conceptually there, it doesn't matter. The flow of control can't reach that point. Okay, that's good. Another thing I didn't concentrate on, I was thinking I would like to feature it, but we ran out of time, was there these things called eval. The other one is, I think, called exec. I'd have to check that in a second. But these basically take strings that are Python code and evaluate them as if they're a Python expression right now. As if you encounter that expression right now, or as if it's evaluating this statement in Python. Now, that may sound weird. I mean, why not just make it a statement in the program? Why not just make an expression in the program? Why are these more interesting than that? They're executing a string. They're evaluating a string like it's an expression in the program. Why is that any better than just having it in your program? Because you can create that string at runtime. You could have that string come in from someone who enters, based on someone's entry on a web search form, it could pull together this string, which is then executed. Now you have to be rather careful about that. But it could read it from a database, right? And patch it together and have it do something, and have it create a bit of code that will do something interesting. You could go and you could take an HTML page and you could turn it into Python code to be executed in a certain way that will strip out certain information or what have you. The point is, now we can treat our program as data. We can go back and forth from data, turn it into code, run it, and actually get values back and turn it back into data. So it kind of blurs this line between program and data in a really fulsome way. And that power comes with responsibility. It has dangers. It has dangers for security. It has dangers for understandability of the code base, as does reflection and aspect-oriented programming, for example. Okay, so Python. Those are some features of Python. There's some really nice things in Python, just like there are in Scala. Comprehensions, generator functions, these list comprehensions that can pull together a collection using very terse syntax and so on. And we can cover those later. But those are some features of Python. And one of the reasons it's a very widely used language. Java 8. What are some features of Java 8?
Streams.
Okay, so, and what particularly about strings?
Streams.
Oh, streams, okay. Streams, indeed. So we emphasized a set of new constructs. Streams, options, for example. And in general, the presence of collections that support functional programming in the form with function types and and support for things like mapping, reducing, and filtering collections. And you could create these so-called lambda expressions, which are these so-called anonymous functions. But as in Scala, as in Python, Java 8, it would be a mistake to view, so we spoke earlier about higher order functions being things that take in functions and return functions. And I just spoke about how you could put together functions in Java 8, just like you can in Python and Scala, with nice syntax. They can be anonymous and you can put them together. But they're not just functions often. They're what? They're not merely functions alone. They're functions which know how to get access to the data they need to do their job. So there's a function, but it knows the values of certain of the variables in it which aren't given to it as arguments. So certain things, this function is given as arguments to it, A, B, and C as parameters. But there may be other things that depends on a D, which is not provided there, and it knows what value, it remembers what value to use. And when we have a function that remembers the values of variables, what is it called?
Closure.
It's a closure. Closure, okay? Function that remembers here the values that it needs to use. And this is a prominent feature of these three languages here. These guys here, that you have these closures. And ladies and gentlemen, it's that ability to remember these things that makes them so much more powerful, makes closures so much more powerful, makes these functions so much more powerful than in something like C, where we have these pointers to functions. I mean, after all, pointers to functions, like passing in a function as an argument, I mean, tells you what function to use. But what pointers to functions lack is the ability to tie that up with the data, certain data that's needed. So sure, they can throw global variables or something, but we'd really like to often pack up a function with the information it needs to operate. And that's what's provided by all three of these. And it's a very, very powerful feature, ladies and gentlemen. And one of the features that exploits this, it's not the only one, but it shows it rather directly, is an important feature. And it's an important concept, it's an important type of action, operation, and that's called currying. What is currying? Anyone remember? So suppose I curry the plus function. I want to curry it. What does that mean?
Abstracting the functions from the function so that it goes back into it.
Okay, so I heard some nice features of that. So let's unpack that. So if I want to curry plus, what's the result of currying? So you curry something that takes
If you've
one or
got a
more-
plus
two or more arguments.
and you just give it one integer, for example, then it'll return another function that takes another integer that gives you the result of that addition.
Okay, so good, and let's explicate that a little bit. So if I curry plus, I'm gonna curry the plus operator, and what I get out. So plus, I could write it as this way, right? I could say plus is something that takes one integer and it takes another integer, so it takes a pair. And the way that's traditionally written is a cross. It's not there's not an X. This is a sort of a cross symbol. So it takes a pair of these. Maybe I'll write it just to make it less confusing. I'll say you take a pair of these normally and you return an int, right? That's what plus does. Its job in life, it takes two things, returns an int. And we'll call this thing A and this thing B. The first argument A, the second argument B, all right? So currying plus is going to return what? It's going to return or what is it going to take? What is currying a plus, what is it going to return back?
an integer or some form of number.
Okay, eventually you're going to get a number out of it, but first you got to get back something. So if I curry the plus operator, what do I get?
It'll take one integer, increase an integer.
Okay, so I'll get back a function. I will get back a function that will do what?
Takes another integer.
It takes an integer. It takes a, right? It's going to be taking a. So curry plus, curry is a higher order thing. It takes a function n plus and returns a function. But the function it returns is a very special type of function in terms of relationship to the function it took in. So here, we'll call this thing that's applied to f, right? So currying of a plus, f here is plus, it's going to return a function which takes the first argument to f, a, which we've called a here, right? And given that, what does that return?
Another function?
It returns another function. Oh man, it makes your head spin, doesn't it? It returns a function which is going to do what? So this guy is also a function, okay? And what is that guy going to take?
So it's our integer b.
It takes the second integer, the second argument of f, b. It's going to take b, and then what is it going to return?
Integer.
An integer. Okay. So there we go. So this currying of this guy ended up returning a function that it returns something, it kind of breaks it into pieces, right? First it takes the first argument, then it takes the second argument, and then once it's got all those, it does its job, right? But the interesting thing is here that this result of currying plus, I mean, what's the benefit of that? It seems bizarre. I mean, it seems like doing extra work. Well, not quite so simple.
Sometimes-
Actually, what's that?
Sometimes you only have one integer at a time, so you sort of want to give it to it. And then
Exactly. Maybe you want to add some number to all these things across each element of the array. So what you do is you curry plus. And you take that and you give it, the thing you want to add to each element of the array. And you get back something that's a function whose job in life is to add 1,000 to everything. Gets a number in, we'll add 1,000. It gets another number in, we'll add 1,000 to it. So it's kind of specialized for A. So maybe we do this, we get out a function, and then we apply it to 1,000, and that gives us back a function. So we gave it 1,000, it gave us back a function which takes B, which takes the thing to add it to, and adds 1,000 to it. In order to do this, it needs to remember here what A is inside of here. This guy here has to be remembering what A was. Say 1,000, or is it 500, or is it 0 or 1? That matters. So this currying returns a function that takes the first argument, and that returns a function that takes the second argument and applies the original function f, here plus, to that first and second argument. Does that make sense? That makes sense? That's what currying does. Now, currying is an example. It's just one example, and it's a particularly mind-bending example, perhaps, of this idea of a closure. But it shows how, this guy here, this is the result of applying f of a and b. This isn't any old int. It's the result of applying f to a and b. That's what that is. And in order to do that, it needs to remember what a is, right? It needs to remember what a is here. And here it's got b, but it needs to remember a. This is what we call a free variable. It's not bound as part of these parameters. It's from outside here. It has to remember what a is. And that's what you can't do with a pointer to a function. Pointer to a function, just it knows, it's a pointer to some function, which takes some arguments, and if it depends on anything else, it's got a dependency on global variables. which is a most unpleasant prospect for reasons I won't go into. But the point is that this is an example of a closure. This guy here, it's a closure. It's not just a function, it's a function that remembers A. Remembers the first thing given to it. Does that make sense? Okay. Okay. So, closures are important, but I also want you to see currying, because you are responsible for currying. Okay?
Hint, hint.
Take note. I mean, I understand that that's not an easy concept, and I understand that if you were to review the material, you might wonder reasonably, is this something we're responsible for? Because it takes a bit of time to get your mind around it, and it is something you're responsible for. Okay, it's one of these more demanding conceptual things. Okay, so currying is something. It's a higher order function. It's an operator. It operates on one function, takes in f, and it gives you back another function that relates to f, but in a very defined way. Sort of like an operator that takes in a function and returns its another function that's the derivative of the original function, right? Those are kind of operators. Okay, so Scala, Python, Java, 8, all support that. In a way, ladies and gentlemen, that would be rather painful to implement in Java, pure, traditional Java, or for that matter, Java's ancestor, venerable ancestor, C. Cross-language comparisons. I have a slide that we'll probably get to on performance. There's a lot that can be said on performance, but there's a lot can be said for ease of expression as well, for cleanliness, for sort of minimalist syntax. There's a lot can be said about interoperability, and a lot can be said about the ease of performing certain types of tasks with particular languages. There's things that can be said about sort of the libraries and how much they perform for a language of certain types of what they provide in terms of support for certain types of tools. So that's good. And in general, I talked about this notion, ladies and gentlemen, of what I called metalinguistic abstraction. The idea is that, when we build programs, we as computer scientists are in this kind of unique position where when we try to solve a problem, not only can we choose which way to go about solving it, but we can define abstractions. We can define sort of structures that have generality and can solve this class of problems. We can build up, in fact, ways of characterizing problems using novel languages that allow us to frame a problem in very clear terms and then solve it. One of the most important ways that we solve problems in the world is to be clear about what the problem is we're trying to solve. And in computer science, we can actually design languages which are nice for expressing certain types of problems. And I would argue that each of those three languages, and many more, have these kind of areas where they've been designed, honed to try to address those sort of problems. Okay, so we have an opportunity as software developers, and you very likely in your career you will be almost inevitably these days mixing languages. At the least you'll be mixing languages like Java and SQL, right? Or JavaScript and some server-side programming language. Maybe it's Django and you're using Python. Or maybe it's Java server pages and you're using Java. But it's kind of rare these days that we'll just sit and only use one language, COBOL, or only use Fortran. The days of that are past. So a lot of where you're going to gain real strength is by picking your tool carefully. You know the old adage about you don't use a hammer for all problems, right? You pick your right tool for the job, and that's what we need to do when we're undertaking professional jobs, is pick the right tool for the job. And if you get stuck on one tool only, you've shortchanged your opportunities. You may have multiplied by a factor of 2 or 3, or worse, the amount of effort it will take to solve a certain problem. And in some cases, it might be, completely inviable. I mean, you're going to get not very far if you try to use Visual Basic to write web scripting and on the server, the client side these days. There was a time where VB Script was used in certain browsers with 2-letter names, but those days are past. So we don't often have that much choice. We are in a multi-language environment, and we need to have a sense of what type of language is best for what. Aspect J. What about Aspect J? What sort of problems is that really a nice fit for?
You've got a certain line of code that calls out to certain things, spread out throughout the code base.
Good. So it's where we have cross-cutting functionality. It's where we have things of a certain sort that are not modularized through normal programming constructs. They're not limited to one function, or a set of functions that call off to each other in a nice hierarchical way. They're not limited to a certain class even, or a set of classes. Instead, they're spread, a small set of interlocking classes. Instead, they're spread through the code. Give me some examples, the sort of things that might be like this. You find them in many, many different areas through your code base. Logging.
Update screen.
Updating the screen. Logging. Tracing. Security-related things. Things related to transaction management. There's a number of types of things that are not limited to one particular subpart of your program, tightly defined subset, but throughout it. And if we want to embrace this notion of a separation of concerns, where we have different types of concerns captured in different areas of our program, something like Aspect J provides us a way to capture these cross-cutting concerns in one place. Now, that's nice. Okay, we put them in their place, and it's neat, crisply set aside. That's good. But why does it go further than that? So we have our existing program and we can find these things in one place. That's actually that doesn't express the full power of aspects. What's another nice feature of them? Well, in the aspects we encode rules, as it were, using what are called point cut declarations and advice. We encode rules for where this sort of code should be woven into our code base. So rather than just weaving it in different places with merely implicit rules about where this goes, those rules become explicit in the aspect. Become very explicit there. And what that means is, amongst other things, it's easier to understand those rules. And if we change our code base, if we extend it, we don't have to depend on the vagaries of our memory or convention to determine where they go. They will be woven in, as long as we have the appropriate point cuts in place with the appropriate signaling conditions. So that's an important aspect of aspect-oriented programming. It provides for not only modularizing, sort of compartmentalizing the code, but keeping the code cleaned up over time as it evolves in a way that makes the rules for how things come together explicit. Okay? Has some risks associated with it, with obscurity. In fact, you might not know this is where the code is being written, being woven in, etc. And some of the tools that are used for aspect-oriented programming, like aspect tools in Eclipse, try to help address some of those concerns. Okay, now a big emphasis that I tried to place was the benefit of using specifications in interface-based programming. The idea of separating the interface from the implementation and having a specification of that interface that uses less ambiguous language and doesn't merely rely on the name of a method or name of a function to communicate it. It's an intention revealing interface, meaning in comments often, sometimes in formal ways of specifying it, we make clear what the contract is. That's a key word here, the contract between a class or method and the users of that class or method. There's a contract. You give me this, I'll give you back that. I maintain this invariant. You can always count on this being the case. Or I maintain this history property. If you look at my value at this time and at a later time, they will compare in this sort of way. What's an example of a history property? How about a particularly simple one? It's almost a gimme if I do this on the exam. I have a history property that's violated. It's super good. What's sort of a simple history property? It's pretty common. In fact, we had a whole lecture about these types of objects that maintain this sort of history property.
Oh, superclasses.
Okay, superclasses that are value objects. So when we have a superclass that's a value object, the subclass also has to be value object. What do I mean by value object? It is immutable. We treat it as a value, like in pi, or 2.71, or 3, or the letter C. These are value objects. They don't change. We don't have references to it, and it gets updated, and over time. We might have multiple references to a value object, but as far as we're concerned, it could be to one copy of it or multiple copies. It's the same thing because it doesn't change. Value objects. And ladies and gentlemen, value objects have an invariant. What's their invariant? Remember, an invariant expresses history property. So an invariant expresses a property that's always true at any one time for an object. A history property expresses something that holds true between two different times. So what is the history property, particularly simple one, associated with value objects?
Oh, it's the same.
It's the same. It never changes. So if you know its value at time t1, its value at time t2 has to be the same.
Another example of a history property is its value might only go up, so.
That would be a history property,
Yeah,
that's right, of
another
a mutable type of object.
Immutable object.
Yeah, exactly. So value objects are objects whose observable features don't change. Secretly inside of it might have some caching going on, or might rebalance a tree or something or might balance a tree or something like that. Might actually do some things to make certain operations very quick that are being done, and as long as you can't tell that it's changed. So a value object, we say it's immutable, and what we mean is, for all intents and purposes, as much as the client can tell, it's immutable. Internally, there may be things changing, but we can't see it. It doesn't change its functionality. Okay? So I talked about specifications in interface-based programming, and they're key concepts, ladies and gentlemen. We talked about abstraction by parameterization. Abstraction, ladies and gentlemen, is about hiding details, and it's about generalizing, going from particular examples in isolation and solitude to going to a general sort of thing that spans all of them. It covers all of them. It covers many cases. And there's two basic ways that we can do this very easily. One is by parameterization. We take a construct and we parameterize it. And so then we can reuse it many places. So instead of having in our code, a thing that calls to a function that, performs the lookup of the ticket price to go from this airport in Saskatchewan to this other one, this pair of airports, Saskatoon, Regina, and another function that's Regina, Saskatoon, and another one that's, Saskatoon to La Ronge, and another one that's Saskatoon to Key Lake. Instead of having functions specific to each of those, we have one function we pass in on the city you want to start in, the city you want to end in, and it will compute any of those, right? We parameterize. Instead of having these functions that don't take any parameters that just are specialized to a certain pair of cities, now we have a function that takes in parameters that says what city you're coming from, which you're going to, and it does the appropriate computation. That would be an example of abstraction by parameterization. We've generalized the situation so we can reuse it in many places, right? Mm-hmm. That has real advantages. We don't have to maintain separate code bases for the Saskatoon to Regina and the Regina to Saskatoon and the Saskatoon to La Ronge. We don't have to fix the same bug in each one, etc. We don't have to duplicate the code. We're reusing the code. Okay. Obviously this is a simplified example, but the point is that that's an example of abstraction by parameterization. We take parameters and we handle many cases because of it, right? The other one is abstraction by specification. So there, we write out an interface, a contract. Maybe it's in the form of a Java interface. Maybe, interface construct in Java or Scala, or maybe it's an interface talked about with specifications purely in comments. But we write out a contract, and then there's many particular things that can implement that contract, right? There's many functions that will implement the sorting specification. So there's a specification that says sort, and it promises back. You give it an argument, and it'll return back a sorted version. Give it a collection, and it'll return back a sorted version of that collection. But there's many ways we can implement it, and all of them would be able to match that specification. Does that make sense? That is a different type of generality. It can handle either of these implementations. That allows us to plug in one implementation for another as we evolve the program without breaking everything out there. Because the things out there are only counting on our specification. They're not counting on our details. We only promise them certain things in the contract, and they don't have to worry about all the vagaries of what's going on inside, right? I argue it's like FedEx, right? Right? So you have the FedEx contract. You can look up online when you need to deliver your package. You can look up online when they'll deliver it. You can look up online the price and everything. And you don't have to worry about whether they use a dog sled or a go-kart or the Blue Flame or whatever to deliver this thing. They could be using a rocket, and it's fine for you as long as your package arrives there the next day. And you don't have to worry about who the employee is, who's in the back office or anything. You don't have to worry about what computer system. They just, as long as they adhere to your contract, you're fine, they're fine. Contracts decouple interface from implementation, and they allow, therefore, separate evolution. You can evolve this component without breaking all those components. Make sense? Key concepts I want to emphasize. And out of that comes the importance of the Liskov substitution principle when it comes to subtyping. We'll get to that, but that's a key sort of follow-on, key corollary to it. Okay? So if we have a subtype, a supertype that adheres to certain promises, if you want to set up a FedEx franchise, you need to abide by the FedEx rules, right? If you set up FredEx and it violates those rules, maybe it mashes the packages in a rude way, or maybe it launches someone a rocket to the moon, or maybe the dogs on the dog sled eat them, or maybe they just don't get delivered by the right time. It gets delivered by the next year, right? Someone could say, you're not a FedEx, you're a fraud. I'm counting on FedEx. I came here, I thought I was getting FedEx, and now you tell me that my cookies that I was sending to my kid in summer camp got eaten by the dogs on the way. That would be say, you're not Fred X, you're a fraud, right? That would be legitimate. And hopefully you'll never be accused of quite that level of abdication of your duties in your software engineering careers. But believe me, you won't get cookies sent to you if you violate the list-up substitution principle. If you're lucky, the cookies will get eaten by the dogs. Maybe you'll get eaten by the dogs. So you got to really watch out, okay? The point is, people count on contracts. And if you have a contract that they're counting on with a supertype, subtypes have to refer to it. Because for all the code knows that's dealing with supertypes, that's the only thing it knows. That's the apparent type. All it knows is that it's dealing with FedEx. And you're saying this is a FedEx, so they're counting. You're giving it something it thinks is a FedEx, and it's secretly a fraudulent FedEx, they're in trouble. So, but if you have a student that is supposed to adhere to the promises of person, but it doesn't, and they're manipulating it as a person, they're going to be in a bad way, because they're counting on it having all the features of person. Their code could have been written long before your code, and you can't willy-nilly break your code by introducing a different class. Okay, let's continue on. Okay, aspects. Okay, yeah, so big picture idea. Performance trade-offs between languages. I have a big slide in this, and I'm going to defer that discussion until later. Okay, functional programming and mutability. That's value objects. Basic operators, and I talked about mutable and immutable objects. And even if you're building an immutable object, it's easier to build it even if you're building a mutable object, either a mutable object or an immutable object, either one, it's easier to build it out of immutable pieces. Why is that?
Immutable?
So if you have a mutable object that you're building, a data structure that's mutable, even then, it's easier to have the things within it. If the things within it are immutable, it's actually easier to reason about, and it involves less work. Why is that?
Because the base of it is not going to change, so it's going to be the same.
That's right. And even if you're building something that's mutable, you have to be careful about giving out references to those pieces inside of you. Because if someone externally changes, you're not going to know it automatically. You're not going to know it automagically. Okay, so with mutable objects or immutable, it's easier to build them out of immutable pieces because you don't have to worry about giving out references to those things that are internal. You don't have to worry about cloning them if the references are passed in. You don't have to worry about serials, about sort of locking issues with multi-threaded programming. Not nearly as much for the pieces that are immutable. They won't be changing, so you don't have to worry that one thread's going to be halfway through writing them when the other one reads it, and bad things happen. Okay, so it turns out that immutability really can simplify a lot of things, including parallelization. Say subclassing and subtyping. Okay, we talked about list-up substitution principle with FedEx, FredX, and the dogs that ate the cookies. Let's talk about subclassing. What does subclassing provide beyond subtyping? So I have a class which implements an interface, an instance. So this class implements an interface. So an instance of that class is a subtype of that interface, meaning I can pass it around as if it, for instance, as if it, to a variable whose parent type is the interface. What does subclassing give beyond just implements, for example?
Subclassing can extend functionality.
Extends it. And let's unpack that a little bit more. When I say it extends it, what does that mean? It means
You're getting more features than the contract and superclass.
Okay, yes, that's true. I'm getting more features in this contract because I am not only adhering to the promises to the contract of the super class, but I am further reusing the implementation of that superclass. So we use the term inherit, right? We inherit that class, right? We inherit from that class. And that inheritance, yes, it comes along with subtyping, because A is a subclass of B. It can be passed around like a B, right? But it's more than that, ladies and gentlemen. It actually reuses the implementation. So suddenly A gets all of the methods of B, all of the fields of B, right? It's a subclass, not merely a subtype. So yes, it can be passed around like a B, and that implies the list-scope substitution principle must be adhered to. It has to adhere to all the promises of a B. But it's more than that. It actually is using how B is implemented. So it's like if you were setting up this FedEx franchise, and now you're told, wait a minute, you've got to adhere to all these promises of FedEx about when you take packages and when you have to get them to the destination. But you also have to reuse FedEx's computer system, and you've got to reuse their transportation system. You've got to use their planes. You've got to use their contractors. You've got to use their package labeling or something. Now there's a lot more complications going on. You don't have the flexibility to use your dog sleds and blue flames. Instead, you've got to use FedEx's. You have to adhere to their implementation. And that involves more complications. What sort of complications come in with subclassing that didn't come in with the list-scope substitution principle?
Gotta make sure that none of the extra functionality add breaks that previously implemented.
Yeah, exactly. Because often we don't just extend it and purely add new methods. We're often, we can sometimes, but often we're overriding methods, right? And just to give an obvious example, if I override a setter for something, probably I need to override the getter for the same thing. Or else, I've changed how the setter works. It's using a different variable, setting a different variable, and now the getter is still using the original variable. And I want to maintain the functionality of this thing, right? Or remember this example we had in class? Do you remember it? A long time ago, long time passing, right? Where we had add and add all. Do you remember that? If we override add, do we also need to override add all? And that was the question. It wasn't obvious. And the interface alone, the normal specification made for people who use instances of the class just wasn't enough. We need to know what? Well, does add all call add? In which case, since we changed to add, it will automatically use our changes. Or does it just do the job by itself? For each and every one, it just does the job of adding, in which case we need to override it too. I don't know if you remember that. I can go through an example. But the point is that we need to know when we're building a subclass more information than if we're just using an instance of this class. We can't just depend on that same interface. So subclassing had some extra complexities associated with it. And that subclassing forced us to deal with these complexities. If we want to allow our class to be open to subclassing, we've got to be extra careful to document some things. What's an example of a thing that you need to document? If you want to build a class that other people could subclass safely, what is something that you would want to tell those people? What sort of information?
Pre and post conditions.
Okay, pre and post conditions are true, and those are, far be it for me to criticize, those are really valuable things to specify. But those would be needed even for instances of the class. Someone wanted to use an instance, they want to create a new instance of that class. You'd want them to know what the preconditions and postconditions are too. They call a method. What does it guarantee? And what does it require? Right? What does it require? What does it guarantee when it's done? So that's true, but I would say that's the same with the list-scope substitution principle. Well, it's true with the list-scope substitution principle. You would want to know those for subtypes as well, to even know if the subtype is compatible with the supertype. Does it adhere to the list-scope substitution principle? But what's a special thing we need for subclasses that they need to know beyond that? Good thing I asked.
If any of the fields of the object are modified?
Okay. So, yeah, there's something very similar to that, Eric. So you might want to know, for example, if you override set, do you have to override get too? Like, which two things use it? And if I override set and get, do I have to override, if they're operating an underlying variable, do I have to override other methods too, which depend on that underlying variable? So maybe this is a class where it maintains an integer, and there's 3 functions: get it, set it, and ask is it positive. Maybe if I override get set, I also have to override is positive, because it also depends on the value of that field. So yeah, something about fields. What depends on fields? What's another thing? Think about add and add all. What's another thing that I would like to be able to tell a subclass so that it can count on it, it can guarantee it? What calls what, ladies and gentlemen? What calls what? Does add all call add or not to do its job? If add all calls add, just a loop calling add, and I override add, I'm done. Boom, game over. That's it. On the other hand, if add all just does the work itself, doesn't call add, then I need to override it too. And the point, ladies and gentlemen, this is a very important point here. It's a very important point. It's a subtle point. And it's parallel to that point I made about aspects a few minutes ago. Ladies and gentlemen, it's not enough to just know right now, does it depend, does add all call add or not? I can go use a decompiler and spy on that, and I can tell probably. The point is, what's guaranteed going forward? Maybe now it calls add, but in the future it doesn't. I want to know if I'm creating a subclass, what's guaranteed for me? Because if it's not guaranteed that add all calls add, I gotta override it. Gotta override it to have my own functionality. That related to that example, and unfortunately because of time I don't have time to hit all these and these important components. After all, we're only on the second slide. Okay, but we're doing a grand tour through this is like most of the important things here. Okay. Many important things are here. Okay. So, ladies and gentlemen, I talked about mix-ins. What are mix-ins? What's a mix-in? We actually talked about them in 2 different ways. But basically, the idea is that you should be able to have the class mix in functionality. Ladies and gentlemen, mix it in. Mix in an implementation into that class from many different sources. So maybe I have a class and I mix in that it's serializable and functionality to implement that. And then I mix in functionality to give it a timestamp, and I mix in functionality also to record the current location. And so I'd like to be able to mix in implementations into a given class. Let's notion of mixins. We see it in Scala using, it comes in various flavors, but we see it in Scala with one construct. And what is that called in Scala? What is it?
Traits.
Traits. It's traits, yeah. We can kind of mix in additional implementations for things, and it's really interesting. We can have chains of implementation where like mix in one thing and then another and then another, and they all get accomplished along the way because one delegates the other to the next, to the next. And I don't require you to know all the details of traits. I kind of underplayed them, but they're an example of mixing. We can kind of mix in this extra functionality into our class so that it has more and more features to it without having multiple superclasses. What are the problems with multiple superclasses? Can anyone say? So suppose here's our class and we have multiple superclasses.
If superclass A has function C and superclass B has function C, which one do you use?
Yeah, so if I have foo here, so suppose I call foo on this guy. So I call, this is O, there's a reference O to this thing here, and I call O.foo, right? Which one does it call? Is it this one or that one? It's not so clear. That's one problem. What's another problem? It's called the diamond problem. These guys, maybe two of them come from person here or something like that. And do they use the same one here or do they have separate copies of it? They may descend from a common thing like java.object or whatever. Do they reuse it? Is it the same thing that they point to or is it different ones? It becomes very complex. And in fact, in C++, you can get in trouble with this. This is called the diamond problem. You can get to it in two different ways, and it's unclear whether these are referring to the same thing or different things. And C++ doesn't do a very good job of dealing with that. Excuse me, it's a C++. If I said Java, it's C++. You can have these multiple inheritance stuff. And generally, it's confusing, kind of dangerous, and mixins give us a much better way to mix this functionality in that's more scalable, transparent. Another nice feature of mixins in Scala, which I should have mentioned earlier, is that when we're allocating an object, we can say which particular mixins we want to mix in with it at that time. It doesn't have to just be a feature of a static feature of a class. Okay? Yeah, that's good. I talked about wrapper classes. Wrapper classes provide a safer way in some ways to accomplish much of what we try to accomplish with reuse. How we try to achieve reuse with subclassing. They provide a safer way because we're not overriding things. What is a wrapper class?
Takes in some other type of object and just does operations on that object.
Yeah. So it actually has a reference to an object internally, and when you call on the wrapper class a given function foo, often it will do a bit of work and then delegate to the internal object. So it kind of passes it through the request, and often it does a little bit more work, like it annotates it, or maybe after foo returns to the inner class, it will tag something onto it or record some information. It kind of intercepts and does some extra work. It mediates between the caller and this underlying class that's maintained internally. And so it will be reusing the machinery of that internal class, but it will be putting a little bit of additional code around it. And it turns out that those things aren't pretty to implement. I mean, they're not hideously ugly. They just have a lot of boilerplate, sort of where take in something, you pass it on to it. You take in something, you pass it on to it. But they avoid a lot of the problems with subclassing, where you override. Where you override, ladies and gentlemen, you can break the functionality of the superclass easily. Because suddenly your code is being substituted in for what their code was. And their code is depending on your code. Can I be very clear about this? This is like an A1 important thing for people to understand. I want to be sure people are rock solid about this, that if you have a class, and this has foo in it, and foo calls bar, this is a superclass, right? Call it B, and you have a subclass A, which overrides B, or so overrides bar, so it overrides bar. And now we have an instance here of A, so we have something that refers to an A, it's an A, and we say, and for this A dot foo, whose bar is being called? Which bar is being called? So I have a reference, it's an instance of A secretly, but all I know is that it's an instance, okay, I'll even, well, okay, suppose I know it's an instance of A. So I have a variable called A, it's a, sorry folks, I'm not more imaginative today. I guess you'd like it more if it were a pineapple or a porcupine, but ladies and gentlemen, if you have an A here, so I know it's, if I think it's an A, okay, and I call A dot foo, whose bar is being called? Remember, foo here calls bar. Whose bar? Is it the bar in B or the bar in A? This is A1 important to understand.
It's likely calling the bar in A, but
It's calling the bar in A.
that would depend on the language, and it's pretty ambiguous.
Okay, in Java, in C++, in Scala, in C#, and basically all those common object-oriented languages, this will definitely call the bar. You're right that there are some other languages of antiquity where actually that's not necessarily the case. But in all these modern object-oriented languages, it's the case. But you're right, there are some where that's not the case. But it's very important to be clear about this, because A is overridden bar. And what that means is the code for foo up here that the person wrote who wrote B, maybe long before you ever wrote A, its code is calling your code. You've like wedged your implementation in. Do you get that?
Need power.
Oh my gosh, thank you. Thank you. Okay. Okay, that would be an A1 bad thing. Okay, so let's pardon me while I deal with this high priority interrupt. Okay. Boom. Okay. Whew. Thank you, Royce. Okay. Okay. Now. Who was that? Is that a happy camper? Yes, it is. Okay. Okay. So, do you understand that? Do you have a reference to an instance of A, even though you're calling here foo in B, and that foo was written by someone else, different person wrote A, because it calls bar, because bar is overridden in the subclass. When you call foo on an instance of A, foo is called here, and it calls the bar in A, not in B. Okay? Now, let me ask this. Just want to be sure you're comfortable about this, because the exam could count on this. Okay? But more than this, I feel if you get out of here and you don't have a good appreciation of that, I would feel negligent and really negligent about not making sure this is part of your education. So this goes beyond 470. This goes to the whole program. Okay. Now suppose that you have something that over here there's a thing called Baz. Okay, and Baz takes in something. All it knows is that it's a B. Okay, it takes in a thing that all it knows is a B. And this guy over here calls Baz with this A, okay? All Baz knows is that it's a B, and this calls foo here. This calls foo. On this thing, all it knows is a B. What's the secret type of this? When you call it with this A, what's the secret type of this thing called B? What is it referring to?
Secretly referring to A.
So it's secretly referring to an instance of A, but for all person who wrote Baz knows it's a B. All they know is they're dealing with a FedEx, right? They don't know that it's this particular FedEx. Just all they know is it's B. So they call foo. When they call foo, whose foo is called, first of all? Whose foo is called? Well, it's the foo, the code for foo that was in B. There's no other overriding. And when it calls bar, which bar is being called?
Bar and A.
Bar in A is still being called because it's truly an A. We say that it's treated like an apparent type, but it's dispatched off the true type. In other words, it's actually calling the true type. The true type is A. It just treats it like a B, but it's secretly an A. And because of that, the bar in A is being called here. Does that make sense? So if you feel at all uncomfortable about this, I would be delighted to explain this and talk with you outside the context of the session. For the sake of the 470 final and so on, I'm counting on you being comfortable with this, but if there's any questions, I'm glad to answer them now. If there's any discomfort with this or deeper questions, I'm glad to have a one-on-one session with anyone. Okay, just to be sure you're rock solid about this, because this is one of the most critical things about object-oriented programming to understand. And it's a confusing thing, admittedly. It's a little bit confusing to people. Because after all, they think this is a B. Shouldn't this be calling this bar? No. You're depending on its true type. Okay? Are we comfortable? Does anyone want me to comment on this more? Okay. No? No? Okay. So if we have a wrapper class, we don't have this issue where if the wrapper class declares a bar, it just when you call bar on the wrapper class, it does some work and it calls the bar on the internal class. So be as a wrapper class here might be, we call a wrapper, and it has a reference internally to a B. Here's a B. It has a reference to a B, and when you call foo on it goes off and it calls foo on this B. And maybe it does some work along the way. Does some more work. This is a wrapper class. You call something on it does a bit of work, and then it calls off that. And if this foo calls bar, it's still calling it on B. We haven't overridden it. There could be, ladies and gentlemen, a bar here, which we define. If we call bar on the B, it will pass it on to this bar, but this foo will still call the bar here in this B. Okay, it'll still call this. It won't call off to the bar here because it hasn't been overridden. Does that make sense? And there's some slides on that in the exam that material in the syllabus. Okay. Okay. Value objects, metalinguistic abstraction. I mentioned those. Architectural patterns. We went through these quite quickly, and they're not going to be played up as much on the final. But I want you to know a little bit about them. This layering pattern. What's a feature of the layering pattern? Architectural pattern. How do higher layers relate to lower layers? So you have these layers, one on top of the other, and how do they relate to one another?
Each layer tries to only communicate with the next layer.
With the next layer down. Okay. It knows about the next layer down. And in some systems, it knows about all the lower layers, but that's less modular. So, if you call something in here, it turns it into a couple calls to things in here. And often there are calls to other things here, which then delegate down. So there can be calls laterally within a given layer. And that calls down to this, and this calls down to that. And these are real things. These are things which operate on our systems. There's calls from user space to kernel space, and then kernel space might call off to device drivers. And you have these successive layers of kind of implementation, which get lower and lower, for example, in terms of their simpler and simpler things going on. Okay, so with layers, you have sort of one layer depending on the layers beneath it, and what's a challenge with layering that comes in? Well, the challenge is if you have lots of errors going on here, the people up here don't want to know about all these errors. So needs to be a way to sort of turn a bunch of these into a few simpler, higher level errors. Because the things going on here may be completely confusing to you. You know, it'd be as if you're, it's not a very great analogy, you're trying to ship something via FedEx, and you know, you get a call from the plane saying, package number 325-244, went out on the wrong pallet. You don't know what that means. I mean, I don't know what this pallet is, what airport, is this at an airport, is it somewhere else? You don't really know about all these low-level details. You don't want to know about all these. What you want to do is you want to know, did this operation complete? And suddenly you've gotten this bizarre, or someone else, imagine if someone called you, you shipped this package, and it's really urgent to get there by tomorrow, and then someone calls you up in the middle of the night and says, Joe is sick today. You say, I'm sorry to hear Joe's sick, but who is Joe? And, he drives the red van. Well, okay. Well, what's the red van? What does that have to do with me? Well, that drives between Pearson International and the Mississauga Depot. Well, I don't know what these things mean, and that's what it often is like at that level. It's like being called and told Joe is sick. And you don't want to be told your package can't get there because Joe is sick. Layering, pipe and filtering. Piping and filtering. So we saw piping and filtering in a couple different contexts. And a lot of it this semester, we saw it actually in nice ways within languages, using constructs such as what? Where do we see piping and filtering exhibited? So with piping and filtering, we have data sources, we have data sinks, things that produce data, things that use up data, and things that process data along the way, where each successive item that is processed is passed down through a series of steps called filters. And they're passed along pipes, right? You saw that when you were yet young in 214, right? With piping on the command line, did you not? Yes.
From you.
Sorry?
From you.
Well, it was my honor to be able to present that, because it's a very powerful concept, we also saw it in the context of programming languages in what form?
Maps and reduces.
Maps and reduces, beautiful, and filters, right? Maps, reduce, filters in the functional context, and then we saw it again in Scala and Java 8 in the form of what? Actually, currying is not a bad. I like that. Was that Peggy? Yeah, currying is an interesting case in the sense that you're providing successive stages of computation, and then work is getting done along the way to a degree. Often we can take currying into this general notion of staged computation, where we actually, like with traditional currying, the work gets done at the end, right? You take each successive argument, and then the work all gets done down here. But as in a generalization of it, you could have some of the work getting done along the way, like work that only depends on A. Maybe it can get done up here when you get A, and then it only has to be done once, right? It only has to be done once. It's already been done here, and therefore, whenever you get a B, you don't have to redo the computation involving A, right? So I really like that, and that would be actually quite similar to pipes and filters. So I would give a thumb up to that with a star, okay? And a gold star too. That's a good one. But there's another thing we had too. Streams, ladies and gentlemen. Streams streams are beautiful. Streams are beautiful. So we have a stream here, and we can, take the first 100 items, and we can filter it, and then we can map, filter it by this certain condition, right? That maybe we take in an X, and we see if X is greater than 0, and then after that we map it, from if we take in an X, we map it to square root of X or something like that, and so on, and we process it. We may summarize it, etc. Streams provide a great similarity to what we see with command line processing in Unix. Why do I say that? Why do I say that? What is it about streams that's very similar to command line processing? Does anyone know? So yesterday I was showing our teenager for the first time. He saw me prodding this Linux box because it was exhibiting dysfunction, and he said, "What's that vertical bar you're putting in there between journal control minus F and molar?" I said, "Oh, that's a pipe operator." And of course, my heart leaped, right? I couldn't help myself, right? I started to explain. To a certain degree, I was probably doing it instead of preparing this. But you gotta, when the student is ready, the teacher will be there. So I needed to be there for him. And one of the interesting things is, did you know you can do that sort of thing in DOS? But do you know what a DOS is?
Yeah. Old computers.
Okay, good. I'm glad I'm not alone. So in Windows, okay, Windows has sort of command prompts that basically run a DOS-like thing. And in Windows, you can use the vertical bar in the shell, but there's a difference in semantics. Does anyone know what it is? Well, it turns out that yes, it's kind of a pseudo pipe. At least this is the way it was in DOS, and I think it's the way it is in Windows, where if you have Command A, vertical bar, Command B, all of A has to execute before any of B takes place. Now, in streams, it's totally different, because this stream does not have to be fully evaluated. In short, ladies and gentlemen, it is what? Lazy. It's lazy, ladies and gentlemen. And I say that here as a compliment. So this stream X, the source of it, does not have to be fully evaluated. This could be a stream that, job in life is to return the prime numbers or something like that, or job in life is to read values off of a sensor, out in a farm field or what have you. And here, each successive value is passed successively down here, just like in Linux. Each successive value is passed down that pipe without requiring the first pipe to totally complete. And there's some really nifty things, really some nifty pipes you can create, sort of these pipelines you can create taking advantage of that, where, the first thing that produced is an infinite stream in Linux of yeses, and you pass it to this, and you pass it to that, and you filter it with this. And it's the same thing here. This could be an infinite stream. We never actually tap here more than the first 100 of them. But the point is, as many of these will be evaluated as are needed, for this pipeline, okay, as are consumed for this pipeline. And here we get each successive value, passed down and then used. It's a very powerful concept, streams. And they allow us to give names to and manipulate potentially infinite or unlimited computations. Does that make sense? Okay. So they're very, very powerful. Okay, so let's go over here and see what additional components here. Pipe and filtering. So pipe and filtering are good. And I talked about a couple of forms of it. One is something called push pipes, and another is pull pipes. What's the difference between them? I talked about hybrid pipes too. Does anyone remember? Push, the source is kind of telling the downstream things here, take this, process it, take here, process it, each successive value. With pull, the sink is requesting the values. With hybrid, sometimes you get a pull from upstream and a push for downstream. But there was another important distinction that I had in place for pipes and filters as well, and that is whether the the pipes themselves, do they have buffers associated with them? Why is that important? Do they have space in them? Because it allows for what?
More efficient use of your time.
More efficient use, and particularly in what way?
They don't have to wait on responses from each other directly.
Yeah, so if they're running in parallel, the upstream and the downstream, they can be operating at the same time with a bit of wiggle room. Now, if the upstream is always faster than the downstream, eventually that buffer is going to fill up all this data to be processed. And it's going to have to wait anyway. It can't go on indefinitely. But, if there's not too many data items that have to be processed, or sometimes one is faster, sometimes the other, you can have a very efficient situation where both run in parallel. They can be doing their things in parallel without a lot of blocking between them, without a lot of waiting. Okay, pipe and filter. Reflection. What is reflection? Ladies and gentlemen, what is reflection?
Function is kind of looking at the methods that exist currently. It's like a step weaker from functional programming. Not necessarily weaker, but less user-friendly.
Yeah, it's interesting you mention that. That's really interesting. That one I got to process, because normally I think of them as kind of two rather separate things, but they do have some things in common. There are some areas of intersection, and I need to muse on that. But reflection basically is about making programs self-aware. Self-aware in the sense that they know their own structure. They can inquire about their structure. They can say, list for me all of my variables, all of my parameters. Given an instance of a class, they could say, hey, list for me all the fields in this class. Or if I'm an instance of the class and I'm dealing with a method in that class, that method could ask, tell me all the fields of this class, and write them each out to a field in the database or something like that. And then if the class evolves by more fields getting put in place, that code automatically runs. Does that make sense? Okay. So that's reflection. And you can also do other things. You could and this is where it gets closer to Eric's point. I think Eric's he's seen something kind of deeply there, and there's really something to that. This link between it and functional programming. But one thing you can do, for example, with reflection is you could determine at runtime which method you want to call, and you can say, instead of having hard-coded call foo, call bar, call baz, call zap. Instead, what you could do is you could have just a string, the name of the function you want to call. Maybe you look it up in a hash table based on some argument, and then you call the function with that name with these parameters. So you can leave it till runtime to determine what thing you want to call. What's inversion of control and dependency injection? I know it sounds unpleasant. Believe me, on the final, you may think it's painful, but at least you're not getting injected with dependencies. So what is that all about?
Inversion of control is like listeners and stuff.
Yeah, it's about going beyond this paradigm. You know, where, and you know, from our earliest education in computer science, we see these things where we write the main function and it calls these things and that calls these things, and some of the things we call are things we write, and some of the things are things from libraries. But basically, it's a very, you know, we're at the center of the control and we're calling things. And ladies and gentlemen, that world is rapidly disappearing in many areas because we're no longer at the center of things. Instead, we plug our code into frameworks. And, you know, these frameworks maybe, we plug it into Spring for a web framework. We plug it into an environment for simulation, like any logic. We plug it in to these plug-in event handlers to a windowing system, and it calls off to us when those buttons are clicked. So the key thing to remember here, the key thing, probably the single most important thing, which I would ask about that, is what's the Hollywood principle? Does anyone remember?
Don't call us, we'll call you.
Don't call us, we'll call you.
Right.
Okay, so we don't have the luxury of choreographing everything. And that's good and bad. I mean, it's bad in the sense that it's not so clear what the flow of computation is. It's not clear what depends on what. We're depending on the system to manage all these things. The other hand, we don't have to do it. It's taking care of all that. It's taking care of the transactions. It's taking care of the persistence. It's taking care of the performance issues. And all we do is we provide a few things that plug into it. And that, ladies and gentlemen, is going to be a lot of your professional life is probably providing these things that get called, you know, by these surrounding frameworks. You write, another example would be you write an Eclipse plugin, and it gets called by Eclipse. So, you know, your code is not the one who dictates all of Eclipse. Thank goodness. You don't have to worry about all of that, right? All you do is you provide this thing, and it'll be called by Eclipse. But having clarity about what's going on around you can be a little bit harder there. So, inversion of control dependency injection. I don't expect you to know a huge amount there, but I do expect you to know the Hollywood principle. I expect you to know that a lot of systems do this now, and it's kind of just like Roy said, it takes the notion of callback, right? You're providing kind of callbacks. But it turns out it can be done, we didn't have time for this, it can be done much nicer in a functional way, and much cleaner, and more beautifully. But alas, the margin was too short for me to write that. I wasn't able to fit that into the semester. But basically, ladies and gentlemen, we have a lot of situations where our code is little snippets that we plug into a surrounding framework. And as you can imagine, that can raise challenges for debugging, for testing, for understanding how it's working, for dealing with performance issues, because so much is going on outside of our code. We talked a little bit about design pattern singleton, where we have a single instance of something and we call things on it. We didn't talk about visitor observer. I'm sorry, that's actually not correct. We talked about flyweight and factory, and there was this little assignment on specification, and I mentioned it in a lecture or two, but didn't really do it justice. What is the flyweight pattern? Well, it kind of uses value objects and reuses them. And it takes advantage of the fact that when you have a value object, you can have many things sharing it. This is one of the reasons why with value objects, we often have to do less memory allocation. Why is that? Because we could share it. We can reuse it. Many things can point to it. We don't care if one thing points to it or 10,000 because it can't be modified. Who cares? It's kind of like if you had pi in your program, you don't really care if Java secretly stores 10 different copies of pi elsewhere or just one. I mean, it can't be modified, so why does it matter? Other than memory, of course. So flyweight, we're basically making a value object that captures certain features, and then we're referring to it for many, many, many different places. And rather than having a totally different object, say for each place in a document, we actually have just a smaller number of such objects that that place in the document refers to. And those are value objects, and therefore they can be reused. So the flyweight pattern allows us to kind of reuse objects from different contexts. Talked about a factory a little bit, and here we have a class often, or a method, whose job it is to create another class, or instance of another class. So rather than directly calling it ourselves, we call something in this factory, and it determines what object to create. Or we call this method. And specification, a specification basically is something that is like a predicate. It returns either true or false. It evaluates the true or false. And specifications can be composed, so we can have ands and ors of different specifications. And those themselves are specifications. And using a specification, we can do many things. For example, we could filter out things that depend on this, that observe this specification, that satisfy the specification. Or we can potentially go and go through a list, and for each thing that matches it, we can perform some action. We can count the number of things that match the specification. So we separate a condition, a rule for whether or not something matches some condition. We separate that out from the underlying code. So we separate out the predicate, the rule for whether or not it's true. And that's useful. We might have some code that searches the database for things matching some specification, then we can pass in different specifications. Specification for things that are big, or things that are heavy, or things that are inexpensive, or what have you. And we can compose specifications for more complex specifications based on ands, ors, nots, etc. Logical components. Okay, so I've just described a large fraction of the important material for the course, but that's not all. Okay. Scala, I thought I owed it to you because, with languages, there's so much you could go into. I thought I owed it to you to sort of tell you, when I think of these languages, what do I think of as things of note and things that might be testable? Okay? I don't want you to, go read the Scala user manual. Well, maybe I do, but not for Tuesday. I'd be inspired if you read that, just as I'd be inspired if you read, War and Peace or something. But here, ladies and gentlemen, I listed some major things. Wednesday. Okay.
No, he's saying he wants us to be done starting by Tuesday.
Yeah. Okay. Well, that'd be nice. But yes, of course, Wednesday. Yes, it's Wednesday. Thank you. Match expressions. It's a multi-paradigm language. I'd like you to know how apply and unapply works. Where does unapply come in? Does anyone remember?
Extract what the parameters that made it would have been.
Yeah, exactly.
Reversing the apply process.
Exactly. What parameters would have made up this object? So we extract these features. And where is it used a lot? In what type of expressions? Match expressions, indeed. Match expressions, indeed, ladies and gentlemen. But it's also used in val expressions, where you say, like, val, this certain a certain object or case class A, comma B equals this thing, and it will match. It will actually get values for A and B. It will extract those values. And I want you to know on what is this applied, and what is it do as a result? Well, it assigns, it extracts the things and it gives them to variables, right? That's what his job in life is. Case classes. What are case classes? Well, these are classes that basically bind together information in a way that makes it very easy. They automatically apply unapply operators and apply. So you can build things. So like you could create a case class for and spec, and specification, or specification. And you could apply it to arguments. So automatically sort of create an apply operator for the class and an unapply operator for the class. And by virtue of that, you can use it in match expressions really, really nicely. Hence the word case here. So you can use it to extract values. And often they're used to kind of hold some simple values in a way that allows you to easily decompose them. Very, very nice little constructs, and they do automatically apply. They automatically define apply and unapply. What are these things called companion objects? Does anyone remember? Well, okay, so you could have a class, sorry, the hour is late, foo, and you could have a companion object, foo. And what does that mean to have a companion object? Well, that's where you'd put static things, like in C or in Java, things that would be static, you often put them in Scala and companion objects. It's kind of it represents the class in a way. And you can use it to define things that can be done statically. And it turns out that you can have an apply operator on it as well. And it's a little bit confusing about how that apply operator corresponds to the one in the class. If you have an apply operator in the class itself rather than the companion object, that apply operator is for instances of the class. If you apply them, in other words, if you say there's a class foo here in Scala. By the way, where do the constructor parameters go in Scala? Anyone remember? They actually go right here up at the top of the class. So double of D. They actually go right up here. Okay, that's where they go. And if we had this, and we had an apply operator here, basically, if we had an instance of class foo called foo, it's an instance of class foo, and we did foo of something, we could treat it like a function call almost, and that's calling the apply operator. Okay. If we have apply in a companion class, I have a slide in this on the Scala lectures, version 3 that I provided you, I think. If we do it in the companion class, if we had object, the companion class here, companion class, ladies and gentlemen, is object foo. That's the companion class, is a capital F, just like this one. Oops, what am I doing? Object foo, okay. That's the companion class for this class. And if we had apply here, A comma B, whatever, guess what this allows us to do? Well, it allows us to write foo of 1 comma 2 or something, and that actually can create an instance of this class with these parameters. So it means we don't have to say new foo. This will actually, it can be used to create an instance of this guy here with this apply operator. So this apply operator in the companion class, this guy here, that allows us to write the class name with these things. This apply operator in the class itself takes an instance of this class and allows us to call it as if it's a method. Does that make sense? Okay. So these are kind of two different two different things. Companion objects allow you to put in allow you to put in static things. Raw and substitute strings. These are sweet things, ladies and gentlemen. These are sweet. What are they?
They don't get interpreted by the.
Yeah, for raw strings, like if you put \n inside it, you don't have to put in \n. You just put in \n. Okay? How about substitute?
Replace the variables that come out.
Yeah, and how do you denote those? Well, ladies and gentlemen, raw ones can be used triple, double quotes, or I believe you can also do R right in front of it here. Substitute strings, you put an S right in front of it. And then what's the difference between that and this doing R like that? What does this create? This is a string. What is this?
Regular expression.
It's a regular expression. Okay. These are different things. You know, listen, I don't want you to have to remember all the details of the syntax, but these are a few things that it's fair game. Okay, so I just want you. I thought I should tell you, so you're just aware of this. And it's useful for reading some code. Yeah, these character prefixes. This guy is sweet because you can have things like, $V in here, and it will substitute in the value of V into the string. It's quite nice. What's the difference between vol and var?
Val can't be, like val's immutable.
Val is immutable. It's just giving a nice name for a value, right? A var, what is that? It's a variable, and so it actually can be assigned to, changed over time. So it's more than a convenient name for a variable. It's actually something that gets updated typically, gets changed. It definitely needs some space to store it. So a lot of the things, if you think about it, ladies and gentlemen, you may even feel a bit shortchanged by all those years with C and Java and C++ and C# and so on, where you had to declare everything as a variable, even if it's just being used like a name, a final variable. I mean, this separates them neatly, and it turns out that that has some nice conceptual advantages and advantages in terms of the language processing. Okay, there's not these kind of primitive types in there, so there's not like a difference. Like there's a lowercase int, but you can't use it to have an array of, in Java there's this whole thing with generics. You can't have this. Why not? Because the handwriting is so bad? No, it's not because of that. Why can't you have this in Java generics? Why can't you have this guy here? Array list of int. Say, why can't you have that? Note the lowercase I. Why can't you have that?
Because with Scala, you don't need to have your types included. So like a Scala that we have, like that would just be a variable, wouldn't it?
So I heard a couple good types of thinking here. The deal is this isn't a class. So in Java 8, this is bad news, and it will be unhappy because this is not a class. And so actually you can't tell it to do that in Java with this primitive value. This is called a primitive value. And so instead you need to give it a, what is it, integer? Yeah, integer like that. And that's actually different. It's a different sort of thing. What's an integer compared to a lowercase m?
It's an object that just contains a primitive.
Yeah, so int actually denotes sort of the actual value, whereas, like it's a value, whereas integer is a reference to that value. And as a result, it requires allocation of those things. In Scala, you can have like array of int, and there's no separation of sort of lowercase int, okay? You can have an array of int. Now you can also, as Peggy says, there's a lot of type inference that goes on where it can actually figure this out in many cases. So you don't actually have to provide it in some cases that it's an array of int. But you can declare I want an array of int, and there's no difference maintained between that and a lowercase int. Okay, there's no sort of separation. Now, this gets into this notion of boxing and unboxing, where in something like Java, we have these numbers, 3.14159, and then we got to put them in a data structure which uses integers. We got to box them up. We got to put them, allocate some memory, put them there, create a reference to it, and then later take them out of there. And there's a lot of back and forth in a way that is stopped with this system in Scala. Okay, traits. Traits allow us to kind of layer on bits of implementation into our classes in nice ways here. And has really nice use of type inference. So a lot of the time you just have to don't specify the types. It figures it out, right? You say val store prefix equals this string, and it knows it's a string, right? And it'll prevent you if you try to do something crazy like take the square root of it. It'll say something that indicates it's bad, and it's got two types of laziness. Okay, the two types I mentioned earlier. Okay, let's just go look here. So Python, multi-paradigm interpreted language. Both are multi-paradigm language. This is interpreted. Comprehensions, I'd like you to know, right? 3 reasons for adverse performance, I'd like you to know. First order functions. A notion of duck typing, we talked about that. You could do first order functions with lambda expressions. You say lambda, x, colon, whatever. I'd like you to know about list slices. What are slices?
You can essentially just put a little block at the end of a list or a string, and it'll extract part of that.
Yeah, so you could say, like, if I have an array, call it ARR. Maybe this is of length 1,000, but I can actually extract, like, between M and N. I can extract this piece, and this is now perhaps a small subset of that array. It'll just be a subset. This means go from M to N. I'm trying to remember, not including N until does one. Okay, I can't remember for sure if this is not including N or includes. I think it includes N in that case. I think until does not. In any case, it can extract a piece of it, and this can be done in a multi-dimensional context as well, where you extract all of one dimension, but only a few elements of the other dimension, and it will go from like a big matrix to maybe, these 3 rows of the matrix, or these 2 rows, or these 3 rows here only, something along those lines. You can extract those whole pieces. That's kind of sweet. Range expressions, so this thing with M colon N. Variables lack strong typing, a given variable, remember P. Importance of indenting and exec and eval. Right? Eval exec, yeah? Okay. Java 8, streams, options, lambda expressions, types for functions. These are a lot of the things that I'd like you to know about. This should be optional. What's an optional, ladies and gentlemen? Why are they significant?
Something that may or may not actually contain something.
May or may not actually contain something. Why is that nice? Well, it turns out that so this is a weird story, but there is a person in the world who's still alive who he's lucky. Maybe he's lucky he hasn't been killed yet. Who invented null? He was the guy who invented null. What null is in programming languages. He invented the concept of null. And he now says it's his billion-dollar mistake. He should never have invented null because it caused so much trouble to have null. And you may ask, well, what else is there besides null? Well, it turns out null has lots of problems, okay? Among other things, you have the same value of null for multiple types of things in C, and so if you have a null vector pointer to a function, or you have a null string reference or a null thing that points to a struct or something, they all have the same null. But what's more is that you can't operate on null, and so often you end up saying, okay, in fact, I saw this in some code. I saw this in code from 371, in fact. I think it was group 1. Yeah. Yeah. So, is this patient's reference null? No. Sorry, it was something like, does the ward exist? Is the ward null? If it's not null, then we'll check if there's a room within the ward. Is that null? If that's not null, then we'll check if there's a bed in that room, which and we'll return the name of the bed or something like that. So it's going through successive levels just in case it's null, and then if it's null, return null. And it was horrible. It was horrible, and I feel bad for them because I know what that's like. You're dealing with all these different possibilities that could go bad in any of these different ways. And it turns out with options, it provides a principled way of dealing with that sort of situation. If there's an absence of a value, you treat it automatically as absence of a value. Otherwise, you do something to the contents. And that gets into your bugbear, which is monads. And I would like you to know some understanding of a few examples of monads. A few examples of monads. I gave some in lecture. One of them is certainly optional. Streams play a role there as well, etc. Some advantages of monads. They're very general, allow for actually quite clear code for doing some things that otherwise involves these successive if this, if that, or that involve quite bad exception handling. It's very clear. It's just you're doing the computation, and if it's the bad case, it automatically handles it along the way. So you don't have a whole other sort of if statements with other else cases or catch statements with other exception handlers. It's all one flow of computation. It's one expression. It's one computation. And that lends itself to clarity. And there's some practical uses of it. Practical uses that have to deal with sidestepping the whole null thing, have to deal with dealing with, for example, maybe you ask for the reduce. Here's a good example. You have a stream and you reduce it, but guess what awkward case could come in? This is our lot as programmers, ladies and gentlemen. We want to think about the common case. That's the case that motivates us. That's the case often which gives the sense of value to the client. But then we have to deal with these awkward cases that we don't want to deal with. We wish we didn't have to. No one told us it would be this bad. When we were in those courses in computer science. Now we got to deal with this awkward case where the user made a mistake or where something bad has happened. Give me a case with streams where you reduce the stream that we have to think about. We're going to reduce the stream and get a number out. We're going to add up the elements of the stream. What corner case would there be there? The stream is... Okay. No nulls allowed here. There's a better way to deal with that than having null. Null was $1 billion mistake. Take it from the inventor. I know I have to deal with nulls too. Okay, but streams have a better way of dealing with it. What do you have if there's nothing in the stream? What do you have? You have an empty stream. If you try to reduce that, what do you think you can get out? An optional. Something is an option value. And it may hold a value or it may not. And with that option value, you could add something to it and get back an option. If it holds a value, it's added to that value. If it doesn't, it just is an empty option. and it can pass it around. So the original computation is still there. It automatically handles this awkward case. And that, ladies and gentlemen, is going to be why your generation may be able to undo the mistakes of mine with null. We introduced null into the world, and your job is to put it back in the bottle. Okay, and options will help you do that, okay? Monads will help you do that. Okay. Monads have very nice support in Scala. I presented a lecture on them, and fundamentally you can in Scala define things that allow you to handle this information nicely. And basically monads are all about packaging up values with some information around them that keeps track of extra things. An example would be whether the value in there is there at all, or if it's just a placeholder value and it actually contains nothing. Another example would be where that value, from whence that value came, or who computed that value, or on what line it was computed. This is metadata, ladies and gentlemen. Metadata about the underlying computation, and you can keep that with monads. It's kind of like a package around a value. The package can keep information too. Okay? I don't expect you to know these in detail, but I want you to have that flavor of things. Okay? And I felt I should tell it to you. Okay? Okay. Performance trade-offs. Ladies and gentlemen, we actually talked about, I regretted once again that I didn't get a chance to come back to this. I didn't have a chance, ladies and gentlemen, to sort of synthesize and bring together multiple threads of conversation that came up at successive opportunities throughout the term with respect to performance. Because, we saw this code, this same code. We saw it in C. We saw it in Java. We saw it in Java 8. We saw it with aspects also being able to instrument. We saw it with Scala, right? That same basic code base. And along the way, we did some performance measurements. We saw it Python. We saw how Python compared with compiled C. We saw how Scala compared with C. We saw how Java 8 did, etc. But there was really no synthesis in a lecture that summarized all of that. And I wanted to give one. But time is short here to give one, but I wanted to bring together many things that we did mention in a diffuse way that you'll want to keep in mind. So when we think about, so part of my goal, ladies and gentlemen, was to get you beyond the mindset, which you will find in a fair number of places, where you say low level, faster, high level, nice, pretty, but slow. It's a common misconception in computer science. You're close to the metal, you use a language like C, and your performance rips along, or you're using a high-level language like fill in the blank, Python, Scala, Java 8 with closures, and it's all pretty, but it's at a disadvantage performance-wise. There's a bit of truth in there, but there's a lot of fiction. There's a lot of short-sighted thinking.
Java is surprisingly fast.
Yeah, and it means going beyond the sort of cherished prejudices and myths that you'll find out there in industry and the occasional person, and actually taking a look at the evidence for modern languages. Actually, there's a lot of people who do realize it outside an industry, but there's also some pockets of diehard C programmers who say C is absolutely needed for the high performance stuff, and you got to start questioning some of those assumptions. And what you'll find is a much more textured picture. And I put down a number of the issues here that I think you want to think about. I mean, one of them is this issue of interpreted versus compiled languages. Which of the languages that we looked at this semester were interpreted? Python. Yeah. Now, there is an interpreted version. You can use a Scala interpreter with Scala. in other words, there's a read eval print loop that you could, if you type Scala, just type Scala by itself, you get it to an interpretive loop, but it's actually compiled. It just allows you to run it conveniently. Okay. Virtual machines. So interpreted and compiled languages. What's the disadvantage of an interpreted language in terms of performance?
It's ridiculously slow because it has to look
Yeah.
at each line and discover everything new, even if it's seen it a billion times.
You've seen it a billion times in a loop. It's like,
Yeah.
what's the first statement in the loop? Oh, it's an if. Okay, is there an else for the if? No, there's no else. Okay, what is it checking? And it's rediscovering the structure every time, right? Or at least that's the easy way to do it. Now, it turns out that really smart ways of creating interpreters can move some beyond that, but generally they have to deal with that sort of possibility because they need to support constructs like eval and exec, which execute strings, and which in a context where you can pull together a JavaScript program dynamically, right? JavaScript's another language, right? I could have used JavaScript. In fact, I hemmed and hawed about whether I should use JavaScript or Python. And I thought I should expose you to Python, because many of you have seen JavaScript before. But interpreted compiled language, that has a quite material impact on performance. There's no question about it. Virtual machines. Which of the languages we talked about this semester run on virtual? What do I mean by virtual machine?
A layer of abstraction away from your operating system.
Beautiful. It's one layer of abstraction. Oh, what's there? Oh, it was there. Away from the operating system. So rather than compile down to the actual machine code, you compile down to a universal binary representation. What's the significance about it being universal? Why not compile down to the actual machine?
Because it's not dependent on the machine it's running.
You don't have to depend on the machine, so you can distribute the same basic code base across different machines. You don't have to worry about compiling it for your particular computer and your other one, etc.
If your Java JVM or your Java code runs on the JVM
Yep.
on a Windows machine, it'll run on the
Precisely.
JVM on
Exactly.
Android device.
Yeah, that's the idea. And actually, there's slight differences with Dalvik and so on, but the basic idea is exactly that, Ross. That's right. That's right. And by and large, for most cases, it's very true. And there's a real advantage to that. All you have to do is they have to ship this adapter, a Java runtime, and it will run it. And all they have to do is put out that for different architectures, and it will run this code base, right? Quite nice. People, whatever machine they're running on, they could grab the same jar files and use them. It's really sweet, actually. Sweet idea. Now, normally you'd think that would be associated with a big disadvantage in terms of code, because it's one layer away from the hardware, and there's an interpreter that goes on normally within the virtual machine to interpret what, to interpret, okay, this is this instruction in the Java virtual machine, now I need to turn it into assembly language. Now I need to turn it into some machine code. I need to execute it. What's this next instruction along in the bytecode? Okay, I got to execute that. Why wasn't that so big an advantage for Java, a disadvantage for Java? You looked at it, right, ladies and gentlemen? Java was faster than the unoptimized C. It was pretty close to the optimized C, actually. Why is that? That virtual machine wasn't more of a hit?
It can take advantage of the fact that it can see the code it was built from. Like it can see the intermediate code.
Yeah.
And make optimizations.
It can make optimizations. And in fact, there's quite a few other of these things that it can do, which are harder to do in C, and we'll come to that. But not only that, it can so this is an example of a smarter interpreter. It's trying to provide the ability to run the same bytecode for this machine, right? Or for different machines. Once you know what machine you're on, there's no use interpreting it every time. It's not like that code is going to suddenly change every 20 milliseconds or something. So what it can do is actually, it can take that bytecode, now that it knows it's on this certain processor, it can turn that on to machine language right now, ahead of time. it can actually cut out the interpretive loop live while the program's running and just translate it once to that underlying instruction set and then just run it. So virtual machines are often made much faster than you think. Give you an example. Another example of this was with virtualized servers. A lot of our departmental servers, you may think, they're installing Apache on the actual hardware over there. These days they're installing it a lot on virtual machines, on virtualized servers. What it means is a given hardware actually has many of these actual servers running at the same time. And they're running on a virtual machine. You know what the performance cost is these days? It's about 2%. 2%. And you can take that machine, you can move it from one machine to another, one physical machine to another. You can upgrade the hardware. You don't have to reinstall it. That is a serious advantage. And for less cost than you think. Another thing is, ladies and gentlemen, you may think Python was a dog for performance for what we looked at. But it's a bit misleading. And I mentioned it in class, but I want to bring home the point. I hope the people over are listening for the rest of the class. It was a dog, but the fact is Python is incredibly important, incredibly valuable for certain performance notable activities, including analyzing large amounts of data. How could that possibly be? If it was that big a dog, how could it be that it's performant for analyzing lots of stuff? Well, the answer is it calls off to libraries which are written in other languages. So, ladies and gentlemen, it's not just about what the language implementation is, it's how big are the chunks of functionality you're implementing in that language. If this code in Python is largely a wrapper around the real functionality, which is written in Java or C or something like that, and it's calling off to it, the performance may be perfectly fine, because it's what it's doing. Sure, it's running in Python, but 99% of the actual workload is in these library calls, which are off to somewhere else. So the Python code performance is actually not bad, because the cost for the Python is such a small bit.
Python isn't the bottleneck.
Python is not the bottleneck. And that's one of the things I said about use of Python for web context, ladies and gentlemen. You think about the Django framework, the very popular framework for creating web applications in Python. Really nice. And you could say, well, it's going to be slow in terms of the scripting and so on. Ladies and gentlemen, if you're accessing this thing over a network, over the internet, if it's hitting the database, it's hitting disk to go to the database and so on, that's not going to be the bottleneck probably. It's probably not going to be that code to render the web page. It's going to be something else in the system, like the network latency or the database latency. The bottleneck is unlikely to be the Python code itself. And it kind of makes sense, because it's unlikely on your web page you're going to have it compute Conway's Game of Life, right? That was an inner loop. That was a very intensive computation we gave it. So it was a little bit unfair to Python. I don't want you to go away thinking Python is a dog and we got to avoid it. Far from it. It needs to be fit for a purpose. And if what you're doing is purposes where the network and the database, etc., are the dominant costs, you probably don't have to worry about Python. It's going to cost, 1,000 times more than the interpretation cost to get the database accesses in for certain web pages. So the script cost, it's small peanuts. The time you save by writing it in Python rather than writing it in another language may pay back in terms of taking that time and putting it into database optimization. That's where you may get the big speed up. So don't view languages as dogs. View them as appropriate for certain purposes, and ask, are they going to be the bottleneck in this case, or is the bottleneck elsewhere? And by writing an X language or Y language, is it possible that yes, it's slower, but it will free up enough time for me to optimize the parts of the system that really matter? And this is something you need to think about in terms of C. Because you could write everything in low-level C and, figure yourself a performance maven, but you'll end up spending such extra time debugging memory leaks and loose pointers and writing low-level code to handle regular expressions when you could do beautiful work in Python or Ruby or Scala or what have you. And the time that you spend, instead of doing these low-level things in C, you could put into those key optimizations on the parts that really matter. And that's another thing we looked at this semester, which was the use of profilers, because those give us insights into where the performance really hurts. And we need to look at things from a broad-minded perspective until we know where's the bottleneck. We don't rush in and say, Python is a dog, we can't use Python, we'll use C. We got to say, okay, where's the bottleneck and this likely to be? If we look at the big picture, where am I likely to get the biggest bang for the buck by investing in what language versus what other one? Memory allocation and management was another big cost, though, there's no question. We have to allocate memory. And this whole thing about allocating your own memory versus allowing for garbage collection. You can allocate your own memory. What languages have manual memory allocation? Think calc, malloc, new, delete. Yeah, C, C++. You can write your own memory allocators. That's powerful. It also takes time. It takes time to get right. And if you don't get it right, it's a lot of debugging time. And garbage collection does pretty well these days. It cleans up for you, figures out what's allocated, what's not, and will clean up. Boxing, unboxing, this whole thing going back between lowercase ints and capital integers can take a fair bit of cost in languages like Java in certain cases, particularly if you have an array of integer or an array list of integer that's very long. It's got to allocate memory for each integer, etc. Allocation of activation records. It turns out in languages like Python and Scala, to create closures, you can't have the stack pop back. You can't have, when this is returned, ladies and gentlemen, you can't have this variable A go off the stack, disappear, and now you're counting on something which is no longer around. So you've got to allocate things in the heap to store. When you make a call, sometimes you've got to store structures associated with that in the heap for closures that get returned. And that can be expensive in certain cases. But a lot of the things these days, ladies and gentlemen, are about this: parallelism and exploiting opportunities for it by exposing dependencies. Ladies and gentlemen, in your lifetimes, your professional lifetimes, nay, within the next 5 years, 10 years, more and more high performance is going to be achieved through parallelization of tasks. The days where our processor was doubling in speed every 18 months are over. And now, increasingly, what we look to is running algorithms, running systems across multiple computational units, running them concurrently. And in order to do that, the languages which were close to the hardware, which were close to the underlying implementation like C, are actually a disadvantage. Because with C, what you really have to consider for parallelism is a couple things. One is mutability, immutability, because of issues with locking. You've got to have synchronization mechanisms and locking to protect two threads from fighting with each other if you have a mutable data structure. If you have a data structure which always stays the same, those two threads can share it just fine. They're happy campers. But more than that, a lot of it is about dependencies. You need to understand what depends on what to figure out what can run in parallel. If A depends on B, you're not going to be able to have A run at the same time as B entirely. If A depends on B's results, B needs to run at least partially first. And as a result, understanding what depends on what is key for programs. And in a language like C, that's really hard to do because you have these loosey-goosey pointers that can point all around. And so taking advantage of parallelism, particularly taking advantage of it automatically, is really difficult. In languages like Scala, Java 8, and with the right libraries, Python, you can do beautiful jobs with this. And it will leave raw C code choking in the dust in terms of speed. So a lot of where big performance trade-offs will be, the battles where they'll be fought, is related to parallelism. And these languages that we've been looking at, those three that I featured, particularly the Python, Java 8, and Scala, those three are notable for providing the benefits, the opportunities for parallelism. And indeed, a lot of what you do with Python for data processing is calling off to parallel processes. And the same thing with Scala. It's really beautiful for it, including for GPUs. Optimization. It turns out optimization is easier if the dependencies are clear. Optimization is more reliable too. Laziness. Well, if you don't have to do this computation unless it's needed, that can save a lot of time sometimes. You just give a promise. Remember we saw that with computable futures with Java 8, where what you give, I should have put that down. That would be something you'd want to know about. Computable future, instead of giving you a value, I give you a promise. And then when you say, hey, I want to redeem your promise, then I give you the value later. And if you never ask me, I don't have to do it, right? Laziness can really help performance as well. Instead of just thinking we'll probably need this, automatically compute it with low-level code, we use a lazy language, which only computes it if needed. Algorithmic design, a lot of the wins. I think all you folks have taken 360 or algorithms classes. Yeah. Algorithmic design is another area where a lot of the real advantages lie. A well-chosen algorithm can often make much more of a difference than choosing C over Java, for example.
Getting log n over just
Totally. Over n, particularly as n goes into the millions or billions, which in your lives, it's going to easily. Already we're dealing with data-rich environments. Companies are trying to mine large data sources, whether it's social media data or point-of-sale data on how their products are selling all around the country, or data from web clicks or whatever. Ladies and gentlemen, a lot of what will deliver value in coming decades will be operating on large volumes of data. And with good algorithms, you'll spare yourselves a lot of computation. But how do you free up the time to sweat this? One of the ways is you make sensible choices about language that don't overly privilege languages which sound low level, but end up compromising parallelization, compromising optimization, not having laziness, and you put the time saved by using high-level languages into algorithmic design. I mentioned the example to you before, but I'll mention it again, of orbits, where so much of the high-level logic was in a functional programming language, Lisp, which was quite non-performant on the face of it. I mean, the same computation in C and Lisp might be quite a bit slower in Lisp, but it was so quick to put together, so quick to evolve, that it allowed them a real performance advantage in the marketplace. And Orbitz is maybe the #1 site now for reserving tickets. And of course, they didn't do the whole thing in Lisp. They'd add large parts of it in highly performant languages for different areas. SQL, yes, for databases, but also for C, for certain types of performant components on low level, C++. So algorithmic design is often where it's at. So ask yourself, where are the bottlenecks of the system, and use tools like compiler or profilers that will give you hard evidence to that. Do experiments, do scaling experiments, etc. So performance implications. Okay, we could go into a lot more here, but I figured that you folks may have questions. So what questions could I answer? You're going to do pretty well if you listen closely to what I've been talking about. there's a lot of fill in the blanks, that you can now fill in the blank on and so on. But what questions could I answer?
When we have to do that little bit of writing in code, are you going to specify writing this code or any of the code being learned in class?
So I'll ask you to write it, for example, in Python or Scala. And again, I'm not going to get really caught up in, if you say lambda of x for Scala code, that won't be a really major ding or something. I'm more interested in, or how you might describe this construct. And the language will typically there be a little bit in the background. I need you to do it in one language or another. I don't want you to spend time doing it in classic Java. So I want to give you some guidance. But really the language, this won't be a chance to test you as much on a language, generally speaking. That's not going to be my goal. Is that helpful?
Yeah, okay.
Yeah. Other questions? Code. I've tried to provide you a fair bit of code. If you notice any missing slides, please let me know. If you would like, so Peggy had asked if I might be able to create some, I think it was Peggy, had asked if I might be able to create some example problems, some example questions. And I'm trying, hoping to get some questions by tomorrow to you, okay? And I will try to see if I can get some office hours before the final where you could come by and ask questions. So I'll try to announce that tomorrow too. If you can't get there for office hours and you really like to talk with me, let me know and we'll set aside some time. Okay, I'll make it happen. I will note that I was asked by another member of the class, Eric Levine, I think, if I would drop by a study section, which is going to be held tomorrow, to answer some questions during like the last hour of it. And I'm happy to do that sort of thing. If you can't make it to that one and you want to have one of your own and you want me to drop by, I'll again see if I can make that work, okay?
It's going to be tomorrow in
371 at 3 o'clock or something, or 4 o'clock or something?
He wants to have it from noon till 4. So
okay, I think it's at 3, I'll drop by, yeah. Happy to do that. Any other things? I know some of you have written about some marking issues with some of the problem sets, and I have an active discussion going on with the marker about remarking some items that were handed in incompletely or appeared erroneously to be handed in incompletely in some cases. And so if there's concerns there, please write to me and I'll check it out, okay? I am happy to share with you some solutions to some of the problem sets and so on in a smaller group context if required as well, okay? Okay, any other questions though? Happy to answer them. I will post these slides. You will find about 50 more slides here, which go into more detail, sort of the next level down from what I've been doing. So, goes into thinking about functional programming, talks about a lot of these things. I expect you to know these, map, filter, reduce. I expect you to know what they do, what their job is, what they take as arguments. And this is cross-language, right? This applies to Python, it applies to Scala, it applies to Java 8. And so this is not about syntax, this is about sort of how they how they operate, currying, yeah, specifications, subtyping, polymorphism, Liskov substitution principle. I'm going to give you some examples of this in the practice problems, so you can try that. If you have trouble, come talk with me. Only one of these things can be checked by a compiler. This guy here, method signature compatibility. But these two things we need specifications for. So methods have to behave consistently, and then history and invariant properties. These two things we generally need a specification.
Quick question.
Yeah.
What are the chances that you can have, maybe not the full set, but some of the problem sets available by sort of noon tomorrow for us to look at during the...
I think the marker is trying to finish those up as soon as possible, so I will get you an answer on that soon. So which ones do you have back now?
Well, I mean, like and some examples to work on.
Oh, examples.
Yeah.
I thought you said problem set. Sorry,
Yeah.
I'm sorry.
I meant-
By noon tomorrow?
Yeah. Just maybe even
Yeah.
just a few, if not
Okay.
the full set.
Okay. If that would that be helpful to folks? Okay, I'll do my best to make it happen. I will go home, and I may take a bit of a nap, and then I may, and then I'll get to work on that tonight. Okay, to see if we can get you some good things here. Oh, this is a very important thing, folks. Remember that most specifications that we write are for people who use instances of the class. In other words, they're for people who are using, when I say an instance, they're using an A, right? They have an A, a thing that references this, and they're trying to, the specifications are, what does foo need to do its job, and what does it guarantee? When it's done, what's guaranteed, right? Maybe it updated the screen in a certain way, maybe it returns the value from a certain computation, maybe it updated some data structure. And that's what I mean by using an instance. An instance specification will tell you what does foo do. But there's a different type of specification. Well, that will make a point. Different sort of specification, which is a subclass specification, which is a specification for people who are writing subclasses. And that is the thing where I said you might want to specify what depends on what, or if you override this method, you have to override these other two methods. If you override set, or get, set, and is positive have to be overridden together for it to be meaningful. Because is, as the implementer, is positive depends on the same variables directly that get and set use. Okay. And there are stricter specifications associated with that. You're providing more information. You're providing information, ladies and gentlemen, about the implementation, not just the promises made. Right? For someone who's calling add all through an instance, do they care if it calls add or not? No, they don't care at all. It could call add internally, it could not call add and just do it directly. They don't care. But for someone who's overriding add, they care a lot. That's why it's a different type of specification. Does that make sense? Yeah. Okay. We care because we're actually inheriting the implementation. That's why we care about it. Okay? Okay. You could see I care about it. Yeah, okay. Right. So there's additional information. Additional information needed. Ladies and gentlemen, these specifications. Man, I feel like Galois on the last night. Oh man. Anyway, I won't go into Galois' story. I was told by a professor when I was your age, I was told he was the best graduate student ever in the history of humanity. Any case, not Galois. Specifications. I got to get this across to you. How do specifications help the person who uses the instance of the class? How do they help to have that specification?
So they know what to put in and take out?
Yeah, they know what it guarantees, right? They know what it needs, and they know what's guaranteed. It's a lot better than just looking at the name and guessing, right? Or look at the names of the arguments, X, Y. Oh, okay. I know it is. In some cases you could do that, but in a lot of cases it's much more fuzzy. You're not sure. Can this thing take a null value for this? I don't know. Can it take a string that's of 0 length? Can't tell from its name, right? So for people who use it at the time that they're building their code, that's really helpful for them. How about as that code ages, as time goes on? Why is that specification equally important, as important for those people who wrote code that uses this? So we said, when they're writing this code, a.foo, they need to know what foo does with clarity. Now, as time goes on, and that code sits around and these things evolve, A and B over here, why does the contract continue to offer value? Guarantee consistency. Beautiful. Beautiful. Because they need to know not only what is the case now, they need to know it will remain the case. So no matter how A and B continue to evolve, at least the contract will stay. Maybe all sorts of things will go on in terms inside of how A and B represent things internally. The internals of their data structures, how they've optimized it. Maybe they go from some inefficient data structure to a really efficient red-black tree or something like that. And that's all fine and good as long as the contract is maintained, right? So for the folks who use it, who use an A, a foo and an A, they want to know that not only something that's guaranteed now, but something that will be guaranteed. So it's not merely enough for them to look at the code base of how foo works and say, it's an open source code base, I see foo does this, so I'm counting on it. Because who knows, maybe foo does it now, but maybe foo 6 months from now will be different. So specifications, ladies and gentlemen, help provide guarantees of ongoing significance. Does that make sense? Okay. Now, how about for the person who writes this code for A and B? Why do those specifications help them when they first write their code? Give me a couple ways. Even give me a way that might have been useful for certain 371 projects.
If they're going to call on the function, they don't need to look at exactly how it's done.
Exactly. So other functions that they're writing might be calling, they don't have to look at all the gory details of it, right? And more than that, with the specifications, they know they're posting information to the user that they're counting on this value being non-null. So the user should be providing non-null values, and so they can count on that. And they can also, when you think about for the software engineers involved, they can write unit tests against these things, right? They can write assertions that will confirm these things. For the people who are writing that code, it provides confidence about what they'll be getting, clarity on what they'll be returning, and a way of testing it right now as well. How about in the future, as these evolve, why does it help for A and B to have specifications? Why does that help them? Help the implementers of them? What value does that offer going forward, that there are these contracts in place? Well, ladies and gentlemen, if you're providing an API, one of your biggest worries when you modify your API is that you're going to break a lot of code that depends on this. You have all these customers out there. You don't even know who they are, perhaps. They're using your API, and you're worried that if you modify this in the wrong way, suddenly it's going to cause their code to break, and they're going to be unhappy campers, and they may switch to a competitive product. They may stop using yours. They may have bugs that make it through to their customers, and they could in conceivable cases they could take legal action. Unlikely, but possible. So the point is that for the people who are writing A and B, they would like to ensure that whatever changes they're putting in place don't break code. And the way to guarantee that is to provide a clear contract. These are the things I guarantee, and by implication, the things not in that contract I don't guarantee. And that gives me the freedom as the implementer of A and B to evolve the system in ways that I know are safe. Because they're not the things that people should be counting on through the specifications. Does that make sense? Because it's very clear to me, as the implementer of A and B, what other people are counting on, and therefore there's things that they're not counting on that I can evolve. By the way, don't be fooled. When you're looking at specifications, you can state in the specification the user should not count on X. They should not count on this search being performed linearly, in one by one. Or they should not count on this class remaining immutable. If you state that, it's fair warning. People shouldn't be counting on it. They shouldn't be counting on that property, and therefore you have the freedom to evolve it. So, ladies and gentlemen, far from being a shackle for the creators of the abstraction, specifications, while they take a bit of work, give you the freedom to evolve it without the worry that you're going to break all this code out there. Does that make sense? Yeah. So those are some important features. Okay, contract and implementation, legal subclass. Okay. Yes. Okay. Wrapper classes. Oh man, it would have helped me. I should have shown this earlier. You wouldn't have had to read my writing. See this wrapper class? You call clear and it calls clear here. You call contains, it calls contains. But the point is, some of these, they do more things. When you call add here, yes, it's going to call add, but it's going to keep track of extra information. And that prevents it from getting in this quandary, the quandary of the other example we had in class, where when you overrode these, bad things could happen because you overrode it in the superclass. Diamond problem. Oop, I saw it there for a second. Diamond problem. There it is. Right. Voiding multiple mix-ins. Implementing small units of functionality. Know it in the form of traits. Okay. I'm not going to go into enormous detail, but you should know traits can delegate in a chaining sort of way from one to the next to the next. It's beautiful. And you can add traits in. You can mix them in with an object when you're allocating it. It's beautiful. Skeleton implementations. Yeah, you should probably know about this. There's an interface list that it's implemented, and then there's I shouldn't say X. It should say abstract list. Ladies and gentlemen, this thing here, it extends a skeletal implementation, and then it just fills in some additional pieces of it here. This is not that important. I'm not going to test this much. But the point is, in Java as a workaround for not having multiple inheritance, you can implement one thing and then have this extends another thing, but it provides an implementation of list in a very easy way by actually delegating to an instance of something that also implements list but is an abstract class, and you just fill in the piece here. This is kind of a poor man's version of multiple inheritance in Java. It kind of inherits from this, and it kind of inherits from abstract lists in a manual sort of way. It delegates to it. A little bit confusing, but you should be aware that this can be done. Okay, yeah, don't worry about DSLs, I'll cut that out. Separation of concerns, layering, okay, architectural patterns, yeah. Okay, reflection, should know about reflection and know that it can be useful for building tools. Very nice for building tools, for operating on languages, mocks, fakes, and stubs, yeah, you should know about that and the notion of mocking. Okay, value objects, yeah. Flyweight, yeah. Singleton, okay, don't worry about aggregates. I'll have to cut that out. And observers will cut out. Hollywood principle, we talked about that. Inversion of control. And you don't have to worry about all these details. I only covered that at a very high level. Yeah, don't worry about this stuff. This will be gone. I don't need to have that in there. You don't need to worry about that. Okay, I need to clean this up. We didn't get to that. Okay, that's it, ladies and gentlemen. If you heard what I said, you'll be quite well prepared. But I will be by the study section tomorrow, and I will try to have that office hours. Okay? Thank you very much, and thank you. Thank you. Thank you. Now, secretly, I'll tell you, I'm going to be in here in this very room marking tomorrow. The final ditch of 371 marking. So if people do want to meet, tomorrow is a possible day for very brief meetings. Okay? Thanks.
Thanks very much.
Yeah.